This is the lecture on work and energy. Power will come a little bit later. If you were absent on January 3rd, 4th, or 5th, this is the lecture that you missed. If you were here on the 4th or 5th and you just want to review, then you're in the right place. To define work and energy, now energy comes in a whole lot of different shapes. Solar energy, the energy we get from food, kinetic energy, remember from middle school, the energy something has because it's moving, potential energy, chemical energy stored in like the gasoline in your car, your engine burns it and turns that chemical energy to mechanical energy. So lots of different types of energy. So it's hard to come up with a really good, concise definition. Work and energy are interrelated, and so I'm going to kind of define them in terms of each other. Work is an activity that changes energy. Oops. And energy is the ability to do work. They both have units of joules. So they're similar. Typically, if two things have the same unit, they're the same thing, but work and energy aren't the same thing. It's kind of like the money in your bank account. You have a bank account, that account has a balance. That balance is kind of like energy, the amount that you have. And if you have a balance, then you can make withdrawals. You can spend that money. You can buy things. Work is like the deposits and the withdrawals. If I make a deposit, I change my balance. If I make a withdrawal, I change my balance in a negative way. So work and energy are related in that way. Deposits and withdrawals and your balance all have the same unit. It's all money, dollars. But they're very different things, just like energy and work are different. But work changes the energy that you have. And if you have energy, then you have the ability to do work. The equation for work is equal to force times distance times the cosine of the angle in between the force and the distance. Now let's look at what this angle can be. Cosine of 0 degrees is equal to 1. So when theta is 1, then, when theta is 0 degrees, then the cosine of theta becomes 1, and this equation is reduced to just force times distance. That's what happens when the force and displacement are in the same direction. If a force and a displacement are in the same direction, so here's a box and this person is pushing this box through some distance and they're applying a force in this direction. So the displacement and the force are in the same direction, the angle between them would be 0. And cosine of 0 is 1, so work simply becomes force times distance. When they're in opposite directions, well, opposite directions would be like, well, the frictional force that's acting on that box. If we take that same box and the person's pushing the box this way with a force through a distance x that's also in this direction, well, the frictional force would work in this direction. So the applied force and the friction force are in opposite directions. That means the angle between them is 180 degrees, and the cosine of 180 degrees is -1. So the equation becomes work equals negative force times distance. When the force that we're talking about, notice different forces can do work. The applied force, this person pushing the box, does work, and the frictional force does work. So when the force that we're talking about, that we're evaluating, and the displacement, the direction of the movement, are opposite each other, then negative work is done. How about if they're perpendicular? Well, I'm going to continue with the same diagram. So we know that that box has weight, and it has a normal force acting, as well as the applied force and the frictional force. And so we've already said the frictional force does negative work and the applied force does positive work. Well, how about the normal force and the gravitational force? So if this object is moving to the right, the velocity, the displacement are to the right, and the normal force is up, or the weight is down, well, the angle in between those would be 90 degrees. So let's look at the equation. Cosine of 90 degrees, if you remember your algebra, is 0. So if I plug cosine of 90 degrees into work equals FD cosine theta, well, I get a big 0 for this part, and so the work equals 0. So if the force is acting perpendicularly to the displacement, that force is not doing work. That's not to say there's no work being done on this box. Out of these four forces, the applied force is doing positive work because it is in the direction of the displacement. The friction is doing negative work because it is opposite the direction of the displacement. And the normal force and the gravitational force are not doing any work at all. To work some example problems, oops, I went too far. If you lift an object using a force of 100 newtons through a distance of 3 meters, how much work have you done? Well, there's our force, and there's our displacement. And if we lift it, we're lifting up, and the object is moving up, so they're in the same direction. Work equals force times distance equals 100 newtons times 3 meters equals 300 joules. If you pull an object a horizontal distance of 10 meters using a force of 50 newtons with a rope that makes a 30-degree angle with a horizontal, what work have you done? So here's your box, and you're pulling it with some force at a 30-degree angle, 30 degrees with a horizontal, and you pull it a distance of, 10 meters? Then F work equals FD cosine theta. The force is 50 newtons, the distance is 10 meters, and then cosine of 30 degrees, and the cosine of 30 degrees is 0.866, and if I multiply these three things together, I get about 433 joules. How much work does the waiter do on a plate of food that's on a tray that he's carrying across the room? So here's our waiter, and he has a tray that has some food on it, and he is moving this way. How much work does the waiter do? So let's look at the forces that are acting. If I do a free body diagram of the food on that tray, there's a normal force, and that's what the tray is exerting on the food, or you could say that the person is doing. The person is pushing up. So that's the person, the waiter in this case. And then, of course, there's the gravitational force down. And again, what else is happening? Well, why is that food moving this way? And what force is making it move? Well, that would actually be a frictional force. If you think about a plate with food on it, if the plate itself moves this way, if there were no friction, like say this was an ice cube on top of a wet plate, then if I move the plate, the ice cube's going to stay put. If I want the food to move along with the plate, there needs to be a frictional force that's keeping the food from doing what it would like to do. The food would like to stay where it is, even though the plate is moved. So it is that static friction force that is actually accelerating the food. So we have this third force, the static friction force, and it is doing work. It would do positive work because it is actually in the direction of the displacement. So forces that are perpendicular to the movement do no work. Forces that are parallel to the movement do work equal to force times distance. Forces that are anti-parallel or opposite the direction of the displacement do negative work. All right. Kinetic energy and the definition. So kinetic energy is energy due to motion. Anything that's moving has kinetic energy. A ball that you throw across the room, a molecule that is vibrating in its lattice structure in a metal, or a water molecule that's moving around in a glass of water all have kinetic energy. Anything that's moving has kinetic energy. The equation that we use is kinetic energy is equal to 1/2 mv squared. It's really easy to use. An example, an object has a mass of 20 kilograms moving with a speed of 10 meters per second. What's the kinetic energy? Obviously, it's a scalar quantity. Why do I say that? Because when I put these things in, kinetic energy equals 1/2 mv squared. 1/2, the mass is 20 kilograms. V, so the velocity gets put in here, and it gets squared. Should have put meters per second in there. So even if it had, this is a speed, so the sign doesn't matter, but if it had a velocity of -10, when you put the -10 in here, it gets squared and it turns out positive. So your kinetic energy is always positive because the only thing here that could be negative is velocity, and it gets squared. So that comes out to be, let's see, 1/2 of 20 is 10, 10 squared is 100, 10 times 100 is 1,000 joules. If you do work on something, you change its energy. That was the definition of doing work. The work energy theorem says that the total work, or the net work, I will say work net, on an object. Now remember, anything that has multiple forces on it has all of these different forces may or may not be doing work. So the net work would be the sum of all of the works that are being done. And the network is equal to the change in the kinetic energy of the object. Or remember, change in means final minus initial. So the change in kinetic energy is the final kinetic energy minus the initial kinetic energy. And remember, if something started out with 0, then the change is just whatever the final is. Okay? So what this gives us is a way to relate force times distance things to 1/2 mv squared things. So maybe we can find kinetic energy without even having mass and velocity because of this relationship. If we know the total work that's done, all we need is that, and we know what the kinetic energy is. And this is an example. In throwing a baseball, you exert a force of 50 newtons through a distance of 0.6 meters. Please pay attention. All of your displacements need to be in meters. All of your masses need to be in kilograms. So if you're given a problem that has centimeters or grams, you're going to have to convert them. Okay. Okay. So back to what we were saying. Force, distance. What's the kinetic energy when you release the ball? Well, because I know that the work done equals the change in kinetic energy, I know that the force I exert on that ball times the distance through which I move while I'm exerting it is equal to the final kinetic energy, because the ball didn't have any when it started. So 50 newtons times 0.6 meters, 30 joules. Okay, so that's, not only is it the work done, that is the final kinetic energy. Okay, if the mass of the ball is 0.1, how fast is it moving? Well, now I can use the relationship that, well, kinetic energy is 1/2 mv squared, so the velocity must be equal to the square root of 2 times the kinetic energy divided by the mass. Okay, I multiplied both sides by 2, I divided both sides by the mass, and then I took the square root. And if I plug everything in, that gives me the square root of 600, I believe. 2 times 30 is 60, divided by 0.1 is 600, and that's about 24.5 meters per second. So there's the final speed, the speed with which you'll let go of the ball. There are several types of stored energy. I mentioned before that gasoline has stored chemical energy. When you put the gasoline in your car, that gasoline goes into your engine, and there's a combustion process, and through that process, the bonds that hold the hydrocarbons together are broken, and that chemical energy in those bonds is released as heat, and it, through a longer process, makes the car go. So there are all kinds of stored energy. The food in your food, when you eat calories of food, calorie is an energy unit. It's not the SI energy unit, but it is an energy unit. So that's what your food is labeled with. That's how much energy you get from those potato chips or that soda or that hamburger or whatever. So all of that is stored energy. And the two types of stored energy that we're going to be talking about are gravitational potential energy and elastic potential energy. Gravitational energy is energy stored due to position in a gravitational field. And around the Earth, that just means energy that's stored because something is above the ground, that it's, if I let go, the gravitational field would make it move. Okay, so how do we calculate it? So the equation part, gravitational potential energy is equal to mg delta y. Now you may have seen mgh, and honestly I might write that sometimes because it's kind of a habit, but really delta y is a better thing to write than h. So we do this, we don't do that, because what really is important is how much the gravitational potential energy is different in one place than another. Not just how much it is, but by how much is it different between two places. And we don't really get that little message from h. So we like the delta y. So I will try to be really good about using delta y instead of h. So this example problem, and I'm going to work it above because of space. A 10 kilogram object is lifted from the floor a distance of 3 meters. How much potential energy does it have? What that maybe should say is how much does it gain? By how much is the potential energy different? So the gravitational potential energy is mg delta y. And so its mass is 10 kilograms. Delta y is 3 meters. It goes from 0 up to 3 meters. I'm sorry, that's supposed to be g. So forget I said that. I'll do the delta y in a second. G, 10 meters per second squared. And then delta y now is 3 meters. It started at 0 and it went up to 3. When I multiply that together, I get 10 times 10 is 100 times 3 is 300 joules. So if I lift something a distance of 3 meters, I will change its gravitational, something that has a mass of 10 kilograms, I will change its gravitational potential energy by 300 joules. Now, earlier in this lecture, there was a problem that said we lifted an object, how much work did we do? It's this one, and 300 joules, we lifted it 3 meters. The work done on lifting this object was a 100 Newton object. That would be its weight. And remember, weight is mg. So this really was mg delta y. And it equaled the work done, but it also equals the potential energy gained by that object that we lifted. One type of energy changes into other types of energy. When we do work, we change energy. And unless something else is acting like friction, the amount of work that we do is equal to the amount of energy gained or lost. Okay, reference level. I talked about this just a minute ago, a little bit. Reference level is what we call y equals 0, the 0 height. And it can be the floor, but it doesn't have to be. Let's say I have a room. In that room, I have a table. Over that table, I have a shelf. I have a box that is sitting on the table. The table is 1 meter above the floor, and the shelf is 1 meter above the table. So if I lift that box to the shelf, and I want to calculate the potential energy difference, well, it is mg delta y is the gravitational potential energy. And it's this delta y that we need to look at. If I use the floor as y equals 0, then the final height is 2 meters. And the initial height is 1 meter. So if I use this reference as 0, then my delta y is the final height, 2 meters, minus the initial height, 1 meter, is 1 meter. if I let this be my 0 height and this be 1 meter, if I let the lowest height that really matters in the problem be my y equals 0, then I find my delta y final minus initial is going to equal 1 meter minus 0 meters equals 1 meter. So either way, the change in height is the same. The amount that you're going to put into the gravitational potential energy formula is the same. So typically, the best choice is the lowest point in the problem. This says consider a child on a swing. If a child is on a swing, that swing goes to the bottom, and then that swing goes back up to the top. And should I consider the grass down here as my level, reference level? Probably not. If I let the lowest point that the swing goes through, I kind of missed that a little bit, be my y equals 0, then everything is referenced to or relative to this height. So now the change in height is just how high this person is above the lowest points. It makes the problem a little bit easier to work. The other kind of potential energy that we're going to worry about is elastic potential energy, and that is the energy that is stored in a stretched or a compressed spring. If you compress a spring, you push on that spring and compress it, it takes work. You have to exert a force through a distance, and it takes work. That work that you do is converted to elastic potential energy in the spring, and that energy is stored. If you let it go, the spring will pop back into its original position, and in this case, it would make the ball fly away. The same thing happens if you stretch a spring. If I took this spring that was initially this long, and I stretched it out to this long, this delta x here, then I'm going to store energy in it. When I let go, that spring is going to pop right back that way. So the energy stored in a compressed or stretched spring is elastic potential energy. I think that we talked about Hooke's law and spring forces back when we did Newton's laws and forces, but just in case we didn't. The force that is exerted on the spring when you stretch it or compress it is equal to kx. K is the spring constant. And it's constant for a spring, it's constant for a spring, but not for all springs. If a spring is really stiff and hard to stretch or compress, then it has a high spring constant. If it's a wimpy spring and you can stretch or compress it easily, it has a low one. Okay, so these look very similar, but they're a little bit different. See the negative sign? This is the force that this spring is exerting, and the negative sign is because the spring always exerts a force that is in the opposite direction from what you're doing to the spring. So in this case, that force that the person is exerting is in this direction. The displacement is in this direction because the spring was this long and they've compressed it all the way to here, a distance x. But the spring itself is pushing back against you. And so the spring and the displacement are in opposite directions, so you get a little negative sign there. All right, so that's the force that you exert, and that's a little bit of a review from what we did when we did forces. But how do I calculate the energy that's stored? The energy that is stored in a compressed or stretched spring, the elastic potential energy, is 1/2 kx squared. A spring at its unstretched or uncompressed distance, the equilibrium position, is kind of like a box sitting on the ground. There's no potential energy. If you do work to lift that box up there, then you give it gravitational potential energy. Work will change the energy. The energy is 0 here. The energy is not 0 here, so you can change the energy. This spring is sitting here. There is no energy. If I do work on, in this case it's to stretch it, I do work exerting a force to the right and stretch it out, then I store energy in that spring. Okay. Total mechanical energy is the sum of your kinetic energy, your gravitational potential energy, and your spring, elastic potential energy. Each of these are mechanical energies. Other energies are not mechanical energies, and so the total mechanical energy would just be the sum of all of these things. This example will not have spring energy in it. The cart is released at the top of a curved ramp. Assume the cart remains in contact with the ramp, neglect loss, so act like there's no friction or drag forces. Where did the cart have the greatest total? Okay, so here the velocity is 0. And how do I know? Because this is a diagram, this is a problem for positive physics. And if this thing were moving, there'd be little action lines behind it. So here the velocity is 0. Here the height, and this is the reference level. They use dotted lines in positive physics. So the height is this value. Where did the cart have the greatest total mechanical energy? Well, we'll get back to that. Let's talk about the other questions, and we'll come back to this one. Where did the cart have the greatest gravitational potential energy? Well, gravitational potential energy is mg delta y. Where is it the highest? At A. Where did the cart have the greatest kinetic energy? Okay, the total mechanical energy is the sum of these. So in this problem, the total energy is the sum of kinetic and gravitational potential because there's no spring involved in this question. So when the object goes lower, it loses gravitational potential energy and it gains kinetic because this sum has to stay the same. The total mechanical energy, if there is no energy loss or added, will stay the same. So potential energy gets lower and lower. That means kinetic energy must be getting higher and higher. So where does it have the least potential energy? Well, it has the least potential energy right there. So if it has the least potential energy, it must have the greatest kinetic energy. So it has the greatest kinetic energy at F. Where did the cart have the greatest speed? Well, it has the greatest speed where it has the greatest kinetic energy, so at F. Where did the cart have the greatest tangential acceleration? Okay, tangential acceleration would be the acceleration, if this is a circle, we've talked about acceleration towards the center, the centripetal acceleration. This is in the direction of the motion is the tangential acceleration. So where is the speed changing the most? And that would have to do with how steep the curve is, how quickly that speed has to change. So it looks to me like maybe it's here because it goes from being steep this way to steep, changing direction over a short period of time. But it could be F. Actually, would have to go back and look at positive physics to make sure what they mean for that one. But see how these are gentle and the speed would change over a longer distance. But these two are pretty tight. I would have to go with G. Okay, so the total mechanical energy is the sum of all of these, and unless there is loss or gain, like if there were friction, that would change it. If there was work done on it, like somebody reached down and gave the cart a shove and increased the energy, then it wouldn't stay constant. But as long as nothing is adding or taking away energy, then the sum is going to stay constant. Well, what does that mean for this first one? Where does it have the greatest total energy? It's equal everywhere. So equal in all the places. The kinetic energy gets big and small. The gravitational potential energy gets small and big, but together they add to be the same quantity. Some forces are conservative and some are not. Conservative forces, if there is a potential energy associated with that force, then it is a conservative force. If there's not, then it's not. What it means in the process of solving a problem is the amount of work done is independent of the path for conservative forces. The amount of work done is not independent of the path for non-conservative forces. So if I have a box and I want to know what the change in potential energy is, or work done to lift that box 3 meters, well, the work done is the same whether I lift it straight up, if I zigzaggy and get it here, If I walk up a ramp to get it here, the work done against gravity would be the same because the gravitational force is down and I'm lifting up against gravity. So the gravitational force is a conservative force because the path doesn't change doesn't affect the change in gravitational potential energy, only the beginning and the end points. Friction, on the other hand, if I have a box and I'm going to push this box on the floor, well, if I push the box straight from here to here, then gravity would do a certain amount of work. But if I'm looking down on, here's me, here's the box. If I push this box in a zigzaggy path to get it here, then friction will do a whole lot more work because friction changes direction as the box changes direction. It doesn't just work in one direction. So friction is non-conservative. The simple form of that is gravity and, I didn't edit this one, gravity and spring forces, elastic forces, are conservative because they have potential energies associated with them and the path won't matter. Friction and pushes and pulls are typically, well, friction is always non-conservative and pushes and pulls are non-conservative. So a student launches a cannonball, neglect the ball's height at the initial time. So we're going to say like this is y equals 0. And identify the energy types present for the ball, the highlighted system relative to the reference level shown. Also identify if loss occurs or if work is done by a non-conservative force. Okay, so right here the ball at A, the ball is sitting there, it has no gravitational potential energy, it's not moving, it has no kinetic energy, and so there is no energy. So if it had a type, we would put the type. B, well at B it has kinetic energy. It also has gravitational potential energy because it is above the reference level. At C, it's not moving anymore. That's its highest point. How can you tell? Because it doesn't have those action lines. And so it only has gravitational potential energy. At the beginning, there was no energy. At B, there was energy. Well, what happened? Well, there was work done by a non-conservative force. There was a little explosion in this cannon, and those expanding gases pushed the ball, and that push or pull is non-conservative, so it added energy to this system. There was no energy, there was energy, something happened in between to make it happen. We neglect drag, and it said neglect loss, and so there is no loss or gain in between B and C. It loses kinetic energy, but it gains gravitational potential energy. So the total mechanical energy between B and C stays the same. The total mechanical energy changed between A and B because this non-conservative force did work. Thermal energy. When the rock in the, I think maybe we didn't talk about the rock in this discussion here, but so we have a rock, and that rock has gravitational potential energy. Let's say it's not moving. It's on a cliff, and we kick it off the cliff, and so that rock falls. It falls and falls and falls, and it gets to a point just before it hits the ground. We'd say its height is 0. It's like while it's coming in contact. And all of this gravitational potential energy is converted into kinetic energy as the rock falls, because there are no non-conservative forces that are acting, just gravity, and gravity is a conservative force. So all of the gravitational potential energy is converted into kinetic energy. Well, then the rock hits the ground and it's not moving. It has no gravitational potential energy, has no kinetic energy. What happened? That energy is converted to thermal energy. I did a demonstration in class showing the conversion of kinetic energy to thermal energy. The example that my college professor did, he had a ladder. Let's see if I can talk through this really fast. He climbed the ladder and he had a bag of, it was lead shots, so little tiny lead beads. And he dropped it, so the bag hits the ground, and a student picked it up and handed it to him again, and he dropped it. Well, I guess before we did anything, we stuck a thermometer in that bag, and it read probably 20 degrees Celsius, which is room temperature. And so he dropped it and dropped it and dropped it, I don't know, maybe 10 times. And then after that, we stuck a thermometer in the bag, and it was like 22 degrees Celsius. So the temperature increased. So the kinetic energy of the rock itself went away, but what happened was all of the little particles inside the rock in this example, or the bag in this example, began to jostle, and the temperature actually goes up. This is an odd thing to do, but in almost every class I've had a student that's done this at some point. If you take a penny, copper penny, and hit it with a hammer a bunch of times, like bam, 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 and then pick the penny up, the penny will be hot, because the work that you do to make the hammer move is converted to the kinetic energy of the hammer, which is then converted to thermal energy inside the penny. I'm going to work through these examples real quick, and then I'll stop talking. Again, we're going to talk about the type of energy present and what has to have happened. Okay, this you can't see because, okay, the ball is up here. It's actually a little higher, but the ball is higher here than it is here. It's not moving in either place. The ball has fallen, and then the ball bounced, and the ball got up to this height. The ball didn't get quite as high as it was. Initially, it had gravitational potential energy. Finally, it has gravitational potential energy, but it has less than it did to start with. So some energy went someplace. So there was a loss at the interaction when the ball hit the ground. There was a loss to thermal energy. That pushing force of the floor took energy from the system. In this problem, at A, the bike is moving and then it coasts down a hill. Coasts, so nobody's putting any energy in. And then the bike's moving, and then they're pedaling as you go up the hill. And then the bike is still moving here. So what kind of energy do we have? Well, here, there aren't any action lines, so it only has gravitational potential energy. It's not moving. Here, it has gravitational potential energy and kinetic energy, because it is moving, see the action lines, and it's above the reference level. Here, it only has kinetic energy. Now, if this were an ideal system, and there weren't any losses or any energy added, then the gravitational potential energy here would be equal to the kinetic, and it would be equal to the sum of these two things. So the totals in these three boxes would be the same. But it's pedaling, and so there's work done by a non-conservative force. When you pedal, you add energy to the system. So pedaling added energy. And in this case, because it's coasting, I think in this problem it said do not neglect drag, and so there was a loss due to air resistance and drag forces. So energy was lost as it went down the hill. There was a loss, negative work done by friction and air resistance, but positive physics calls negative work a loss. Okay, let's quickly get through these. At A, there's gravitational potential energy. The reference level is here, not here. So at B, it has kinetic and gravitational potential. And at C, it only has gravitational potential energy. And I think this problem said neglect air resistance. And there's no energy added to the system. She just lets this thing go. So there is no loss and also no work done. Okay, one type of energy converted to another and then converted back to gravitational potential. I stuck this one in here because it has spring energy. This is a slingshot that's stretched back. The reference level is right here, so nothing has gravitational potential energy in either place. Here, there is elastic potential energy, spring energy in the stretched band, and finally there is kinetic energy because the ball is moving. So in this case, all of this elastic potential energy is converted into kinetic energy. And that finishes today's lecture.